All right, suppose A sub I with I and B sub I with I are index families of sets. For each ordered pair ij and I times I, let C sub ordered pair ij equal the Cartesian product ai times bj, where P is I times I. And then we want to prove that the union over this index set capital P of C sub P is the Cartesian product of these two unions over the index set I. Okay, wow, that's a lot of notation. Let's try and unwind what that might actually mean intuitively. I guess the place to start is with this index set capital I. So just to keep things relatively simple for ourselves, let's take that index set to be just 1, 2. Okay, that is 2. There we go. And then if we're looking at I times I, which is the definition of capital P, well, this could be one copy of I on our sort of horizontal axis, 1, 2. And on our vertical axis, here's another copy of I, 1, 2. And okay, I times I would consist of 4 points, right? Ordered pair 1, 1, ordered pair 2, 1, ordered pair 1, 2, and ordered pair 2, 2. Okay. And so altogether, those 4 points make up the Cartesian product of I with I, which is how we are defining capital P. All right. So you can sort of think of this copy of I down here being the index set for the first union, this copy of I here being the index set for the second union, and then these 4 points here, P, being the index set for this union on the left-hand side. So let's try to draw the union on the left-hand side first. Okay. So we have C sub P, where P is any of these 4 ordered pairs, right? And then C sub ordered pair is really just AI times Bj. So what we really have are, okay, well, first of all, we have AI for I equals 1 and 2, and so we have A1 and A2. So let me draw A1 right here, and maybe an A2 right here. And similarly, we have a B1 and a B2. So do something like this. Okay, and then if we take, for example, A1 times B1, we get this rectangle. And that, by definition, is C sub ordered pair 1, 1. Right? So let me try and write that, C sub 1, 1. Okay, and if we take A2 times B1, we get another rectangle, which we are abbreviating as C sub 2, 1. And then A1 times B2 is C sub 1, 2. And finally, A2 times B2 gives us this last rectangle, which would be called C sub 2, 2. Okay, so for each of these 4 ordered pairs that showed up here, we have C sub that sort of P value. And the union of the 4 of those gives us these 4 rectangles. Now, this equation is saying that that's the same thing we would get by taking this Cartesian product on the right. And the union of the A sub I, well, that's just the union of these 2 line segments down here on the horizontal axis. And the union of the B sub I, that's the union of these 2 here. And, okay, if you take that union, so you take your first coordinate from one of those, and you take your second coordinate from one of these, then you can get any point in any of these 4 rectangles. Exactly, right? So these sets are the same. Well, I hope that was somewhat convincing, at least on an intuitive level, but we need to go ahead and try the proof out. So let's get our goals, givens and goals down here. This one just says that for every ordered pair ij, we're defining Cij to be this Cartesian product, and we're letting P be I times I. And here's our goal, which is just the same thing I wrote up here, but with smaller union symbols. Okay, and then to prove that those 2 sets are equal, we're going to prove that x being on the left side is equivalent to x being on the right side. And of course, I should have a for all x at the beginning here. And the first line of my proof should be let x be arbitrary, but I'm going to leave those off just to simplify the proof a little bit. And hopefully my reader will recognize that those are kind of implied. Okay. All right, and there are my givens. Now, let's go ahead and try to prove this biconditional with a chain of if and only if statements. This is kind of a monster here, right? I'm not sure this is necessarily my recommended way of doing this proof, but I want to show you how it works, so you can see you can do things like this, and then we'll go ahead and prove it again afterwards using the proof techniques we learned in chapter 3. Alright, so we're going to show that x is in the left side if and only if it's in the right side. And okay, we have that x is in the left side, and x being in the union over an indexed family means that there exists some index p in the index set capital P such that x is in that particular C sub p. Right. Okay, and then we know from our problem statement, from our givens, that capital P is I times I, so we can make that replacement. And then this is a bounded quantifier, right? There exists P in here. That's just an abbreviation for there exists P such that P is in that Cartesian product and x is in C sub P. Okay, and then P being in this Cartesian product, we know that the definition of that is we have a first coordinate I and a second coordinate j such that P equals the ordered pair ij with I and j and I. And so far so good. Okay, and then next, you notice this x in C sub P is outside of the I and j quantifiers, but there's no I and j involved there, so we might as well just bump it inside this parenthesis here. It's not going to change our statement at all. Okay. And once it's in there, well, we also have in there that P is equal to the ordered pair ij, and so we can go ahead and replace that P by the ordered pair. Good. Okay, well now we have all of our quantifiers out front, so we can put them all together and rearrange them however we like because they're all existential quantifiers. In particular, we could put the P1 inside, and once it's there, we can pull these three statements outside of that there exists P quantifier because there's no P's there, right? The only one that has a P is the first statement, and we have to leave that inside the quantifier. So we get to this line. And then the cool thing here is, look at this little statement. There exists P such that P equals that ordered pair. What do you think about that one? It's always true, right? I mean, inside of these quantifiers, we have an I and a j, and so the answer is P equals ij. I mean, it exists. So this is actually a tautology, this little piece here. And so we have a tautology and a bunch of other stuff, and you know that the tautology can just be dropped in that situation. It doesn't affect the truth value. Well, the truth value is the same after you drop it. Okay, so we get to here, and from here, definition of Cij is ai times bj. Definition of x in that Cartesian product is there exists a first coordinate a, a second coordinate b, such that x is that ordered pair with a and ai and b and bj. And then let's kind of get our quantifiers together again. These two statements here don't have any a's and b's in them, so we can go ahead and stick them inside these existential quantifiers. And once they're there, we just have a bunch of and connectives, and so we can push the I and the j and I a little further in so that they're next to in this case, the other little I, and in this case, the other little j. All right. Now we can rearrange the order of the quantifiers again and kind of push the I and the j quantifiers inside here and basically attach the I one to the only two statements which have a little I in them, and attach the j quantifier to the two statements with a j. And then what do those mean? There exists I and I such that a is an a sub I. That's the definition of a being in the union of the a sub I. And similarly, this here is the definition of b being in the union of the b sub I. And we are done because this statement is exactly what it means for x to be in this Cartesian product, right? We have that x is an ordered pair where the first coordinate is from this union and the second coordinate is from that union. And so we're done. My goodness, that was kind of intense. So, well, good. That's one way to do it. Again, I'm not sure I recommend that. It actually took me a little while to work all that out. I had a number of false starts along the way. It might be better to sort of stick to our guns and use our proof techniques. Okay, so let's give that way a try. Let's go back to our logic and unwind it a little bit. Okay, so I just cut some things off the top so we have a little more space. So first we're going to prove the forward direction. X in this union implies X in that union, and we can do direct proof to accomplish that. So we get a new given. And X being in that union means there exists a P in the index set capital P such that X is in C sub P. And X in this Cartesian product means that, well, it's equal to an ordered pair AB with A and B in the appropriate sets. And then here we can do an existential instantiation to get P naught in P and X in C P naught. And I'm going to be a little bit sloppy and not write those naughts, okay, just to keep things a little bit cleaner. There's enough subscripts going on already in this problem. So, okay, I really should write P naught here, but what I'm doing instead is sort of magically taking this bound variable P and just making it into a free variable, okay. Hopefully my reader will not be confused by that. Okay, and then capital P is I times I, so we can make that replacement. And for P to be in that Cartesian product, we know we can write it as an ordered pair ij with I and j both in capital I. And now I can do another couple existential instantiations. And again, I'm not going to bother to put the subscript 0 on the I and the j. Okay. And once I do that, I'm just going to have 4 statements connected by an and so I can go ahead and break up that conjunction onto 4 lines. So I have these 4 different givens. All right, well, if P is that ordered pair ij, then I can replace the P down here by that ordered pair. And once I see that, I remember that Cij is just AI times Bj. Okay. So I'm getting closer, if you look where we're headed. For X to be in that Cartesian product means that it's an ordered pair with A in A sub I and B in B sub j. And one more existential instantiation. And once again, I'm not going to do A naught and B naught. Break up the conjunction, and we get that X is this ordered pair with A and B in the appropriate places. And, well, now we just got to say that A and B are in the appropriate unions, right? And so because A is in A sub I, where I is one index, that's exactly what it means for A to be in the union of the A sub I. And similarly, we have B in the union of the B sub I. And again, I'm changing this, this I here is a dummy variable, so I could write I or j there. I'll do I because that's what shows up on this side. Okay, and that does it because if X is this ordered pair with the first coordinate in this union and the second coordinate in that union, then we have shown this, right? For these particular A and B. All right, so let's write this up. So we're doing the forward direction. So suppose X is in the left side. So that's the direct proof that I've already begun writing here, right? So we have that as our given. This is our goal. And from here, the first thing we did was definition and then an existential instantiation to get here. So let's write that down. We'll say there exists some P in P such that X is in C sub P. Okay, and then that meant that actually P was in I times I, and we did a definition and existential instantiation, and that eventually led us to these statements, right? So let's record that. Say then P is in I times I. So there exists some I in I. And my daughter's coming. I need to pause for a moment. I'll be back in a bit. Okay, where were we? So there exists some I in I. Oh, let me just say there exists some I and j, because that's how we wrote it over there, such that P is equal to that ordered pair. Then I is in I, and j is also in I. Okay, and then another replacement and definition of that, and existential instantiation, right? So basically C being in here eventually got us down to this stuff. And so we can say then, well, X is in CP and P is that, so excuse me, little p is ordered pair ij, so we have X is in C sub ij, which equals A sub I times B sub j. So there exist some A and B, such that what X is equal to AB, and we have A in A sub I and B in B sub j. Okay, and then we got our A and B in the unions, right? Using that I and j were in I together with these two got us here. So I will say because I is in I and A is in A sub I, it follows that A is in the union of the A sub I. Okay, throw a space in there. And the next one is just basically the same, so let me copy and modify this one. Because J is in I, and B is in B sub j, it follows that B is in the union of the B sub I. All right, and then that's basically it, because we've got X in, X equals AB, where A and B are in here, and so we somehow end up there. Okay, that we can write X in that way. So let's just summarize by saying therefore, because X equals the ordered pair AB, together with the two things we just concluded in the previous two lines, it follows that X is in this union here times the same thing with the B where the A used to be. Okay, that finishes that direction. We're not going to go through this big dance for the other direction, but let me show it to you and quickly talk through it. It's quite similar to the direction we've done. Okay, so suppose that X is in the right side, we show X is in the left side. Because X is in this Cartesian product, there exists a first coordinate A and second coordinate B in the appropriate sets. And all right, well, if A is in the union, then we have an I such that I is in I and A is in A sub I. And if B is in this one, we get a J and a B and B sub j. And then, okay, well, X is still equal to AB, and we know exactly where A and B are, therefore X is in that Cartesian product, which we are referring to by C sub ordered pair ij. And that subscript there, that index, is in I times I, which is P. Therefore, because X is in here, and the index is in P, that means X is in the union of the C sub P, which is what we wanted to get to. All right, well, that was some work, but I hope you learned from those two possible ways of proving this problem, and that does it.